Okay, I guess I'll get started. Yeah, so today, as I promised, I'm switching gears a lot and going to just discuss a very classical geometric problem, which is the question of trying to find sort of least area surfaces, say, even in Euclidean 3 space that bound a given closed simple curve. And as we'll see, this is not totally unrelated to the rest of what I talked about, since sort of the crucial ingredient will be sort of relating this sort of purely geometric question about area to a question about energy, which, as we saw, energy is somehow, at least in dimension 2, a conformal quantity. So it makes sense in the context of Riemann surfaces. Okay, so to motivate things, I'm not going to start with surfaces. I'm going to start with curves and just make some observations to try and explain when we get to surfaces why we do what we do. Right, so from now on, let's just fix an n-dimensional proper submanifold inside of a big Euclidean space. So of course, by the Nash embedding theorem, any Riemannian manifold can be thought of this way, at least any closed Riemannian manifold. So this just simplifies our life. So what we observe is, if we have a curve gamma that takes the closed interval 0 to 1 to, say, m, right? So again, this is just a curve in Rn, but it's constrained to lie inside this manifold. Then if we have the length of the curve, which is just a geometric quantity, which is 0, 1. And I want to be a little careful here. So what I mean by curve here, so I'm saying this is a parametrized curve. So i.e., it's just going to be a C1 C1 or smooth. That's not so important, but it's a C1 map. So I'm not claiming this is an immersion. So I'm not assuming Right, so the observation you make is, because I'm not assuming it's an immersion, even though the curve might be very regular, the image doesn't need to be very regular. Like, it's possible to write a C1 map that parametrizes this guy, right? It's just that at this point, the derivative becomes 0. Okay? So in any case, the length makes sense, and the observation is that the length is not a function. If you think of it as a functional on the space of these parametrized curves, it's not really a functional of the parametrized curves. It's really a functional of the image, right? So the observation is that if you take a phi, which is just a map from 0, 1 to 0, 1, which is let's say it's a bijection. That's also non-decreasing. Right, then the length of the reparametrized curve is the same as the original curve, right? And this is the point is, right, really this length is a functional not of the parametrization but of the image. Now the point about this is that this has a lot of kind of bad, this is sort of tells us that if we want to study, say, this functional from a calculus of variations perspective, we're going to have a lot of trouble if we think of it in terms of these parametrized curves. Right, so the observations of, because of this, right, say minimizers or critical points. So in general, you expect sort of minimizers of a functional or critical points of the functional to be sort of fairly rigid objects, but these guys are highly non-unique. Right. In fact, you have a whole infinite dimensional freedom by changing the parameterization. Right. So this one of the things this really tells us that if we want to try and study these things analytically is that this means very easily, it's easy to see that this means that the functional L does not control anything about the parameterization. I mean, it might tell you something about the image, but it certainly can't control anything about the actual parameterization. And I mean, just to see that, I mean, consider the following maps phi n of x, which map the interval to itself, just given by x to the n, right? So this converges uniformly on compact subsets of 0, 1. So this converges, uniformly on 0 in the open interval to the function 0. So if you just look at gamma n, which is gamma phi of n, right? Essentially, this just converges if you take the limit to sort of a constant curve at the point. So everything that's interesting is somehow getting shoved towards 1, which is sort of you don't see in the limit. So this means that trying to get any kind of control on the parameterization in terms of L is hopeless. So a final thing, which is a little bit, I mean, it's not really related, but I just wanted to put it out there, is there's an issue of regularity, which is sort of related to what I said. But, right, I mean, we can assume gamma is smooth, and then that would seem to be the most regular situation. But of course, by this perspective, I mean, that's not necessarily regular at all, or even by considering the corner. So of course, I mean, right, the regularity of gamma has nothing in principle to do with the regularity of the image. So the regularity of the image, so the right point of view for regularity from the perspective of the functional is that, so the right is that say the image, so the image of gamma is is some kind of, say, C1 submanifold. Right. So in other words, if you look at the image, then you can sort of locally straighten it out by C1 charts, or if it's smooth charts on Rn, or smooth local diffeomorphisms. But the point is that's not really seen by it is seen by gamma. So this is equivalent to, not that it's equivalent, this is implied by gamma being an immersion that's injective, right? That's a easy theorem. But the problem is that, first of all, it's not equivalent. So you can introduce sort of artificial problems in the parameterization. So you can make a parameterization not be an immersion, even though the image is nice and regular. The other thing is that this is, I mean, neither of these properties are well behaved under taking limits. So you don't necessarily, I mean, you can't use the sort of theory of limits of the parameterization to kind of say anything about the regularity of the image. Okay, maybe I'll try and, this will be, and these sort of show up in the issues in the surface case too. So we'll come back to it. So these are the sort of the issues, right? Okay, so what are the solutions? So there's sort of 2 points of view you could take. So the first point of view, which we won't talk about, though I think is of course to you kind of look at the correct geometric objects. So in this case, the images. So these are supposed to be like subsets of M, or subsets of Rn. And the point is here is if you think about these as objects, I mean, you need to kind of come up with the right framework to kind of take limits and so on and so forth. So one way to think about them is these are, say, closed sets, and there is a topology in the space of closed sets, so you can take limits in the space of closed sets. This is this kind of Hausdorff topology, which is sort of the submanifold version of what the Gromov-Hausdorff topology. of course, the problem is then given like a nice, I mean, the limit of a closed set, I mean, in general, closed sets are incredibly ungeometric and horrible, and so it's very hard to say that that gives you much geometry to work with. Of course, there's other weak objects you could work with, like sort of various measures associated to the image. And this certainly is a very powerful perspective. It's just very technically demanding. And I mean, it leads to this notion of kind of geometric measure theory, which I think is a very... So, of course, we're not going to talk about that because it's quite demanding. But I think, in a way, it gives you a perspective on things that's once you work through all the technicalities, clarifies a lot of things. So the other perspective, and it turns out, maybe I'll mention at the end. I mean, in some sense, at some point, this is at least from the point of view of kind of minimal surface theory. Once you get to high enough dimensions, this is sort of really the only perspective that makes sense. The other thing to do is to look at a preferred parametrization. Right. So this is somehow should be related to the functional. The geometry of the situation, and the idea is this is supposed to cut out all this infinite dimensional symmetry. Right. So again, you did see this in Aaron's course. So in his case, this preferred parameterization was, there's several, but the one that turned out to be, I think, the nicest one is sort of these notion of harmonic coordinates. So of course, in the case of curve. You probably know what the preferred parameterization is, right? So it's the parameterized by arc length, right? But there's a slight subtlety here, which maybe we have to kind of deal with, and we have to deal with it in the minimal surface case too. So I'll maybe emphasize it. I mean, to talk about the parameterization by arc length implicitly assumes you have an immersion. So you have to kind of think about what this means when you're not an immersion. But anyway, this is the perspective we'll take. And the point is, I mean, there's this parameterization by arc length, I can just say, but actually you can kind of see it in terms of the functional in a kind of a natural way. So the idea is you introduce a new functional called the energy of gamma, which is just going to be the Dirichlet energy of the curve. Right, so we just take the square. Okay, so we don't do anything except for put a square instead of an absolute value. But the point is, this right away kills the symmetry. So this is not invariant under reparameterization. So this is really a functional on the parameterization and not on the image anymore. Okay, and so then the observation is that the observation. Right, is that and this is, I'm sure you've seen, if you've taken any geometry class, that the length of gamma is always less than or equal to the energy of gamma to the 1/2, and you have equality. There's equality here if and only if gamma prime of t is constant. So in other words, the constant speed parameterizations are precisely where you get equality in this inequality. So the idea now is that you expect, you certainly expect there should be a relationship between minimizers of this functional and minimizers of that functional based on this inequality. It's also true that there's, and this requires some computation. There's a relationship between the critical points, but that's not necessarily as clear from this inequality. And of course, this is just the Cauchy-Schwarz inequality. This is just Cauchy-Schwarz. Okay, so again, the observation is that you have right. So one observation is that a length minimizing So fix some endpoints, say. Say it's length minimizing if any other curve between those endpoints has at least that much length. So a length minimizing immersion gamma is, well, let's put it this way, can be parameterized, can be reparameterized to be an energy minimizer. And this energy minimizer, of course, is going to have the this is taking the constant speed parameterization. So in fact, the other direction is true, but this requires a little bit of thought, right? Because you could imagine that the length minimizer is not actually an immersion, in which case you couldn't reparameterize it into the. I mean, when it's an immersion, you can see how to make this work, hopefully. But when it's not an immersion, you might have to spend a little bit of time thinking about what happens. So there's actually a very simple way to see this, which also kind of explains some of the issues I mentioned over here. Right? So given any curve, gamma, right, given our setup, like we can define a new curve, gamma sub epsilon, which takes 0, 1, to now think of it as M cross R as a subset of Rn cross R. And what we're going to do is we just send what parameter do I use? T gets sent to gamma of T epsilon T. Okay? Right, so this now is clearly an immersion because we always have non-trivial derivative here, and it's actually an injective map too. So this is actually, the image of this is a really nice curve, whereas the gamma itself, it doesn't need to be nice. But the idea is then the area of gamma epsilon, or the length, of gamma epsilon goes to the length of gamma as epsilon goes to 0. And similarly, the energy of gamma epsilon goes to the energy of gamma. And the point is, I mean, in a sense, you have this nice guy that converges as epsilon goes to 0 to this potentially not so nice guy. Right, but what we've done is we sort of resolved the problem, and now since this is an immersion, we can just make the argument go through that. And since we have this convergence, we can see that in fact, energy minimizing and length minimizing is the same thing. Okay, so then the final remark, which again we'll see this slightly in the surface case. So, right, I mean, one of the things we want to try and maybe do is take a minimizing sequence, and of course, as we asserted that this was sort of made no sense. I mean, to find a length minimizer, you might want to take a minimizing sequence for length, but as we kind of can see by this reparameterization phenomena, right, this can never work for the length functional because we could never hope to pass to any reasonable limit in terms of at least parameterizations. However, by this sort of observation, we could try and find a length minimizer by minimizing energy and taking a minimizing sequence of energy. And then the point is, this is you should convince yourself that something like this has energy that goes to infinity. And so if we have a much more likelihood of finding the energy minimizer, and then we can use this observation to say that it has to be a length minimizer modulo some regularity issues, which I don't want to get into. But I just want to point out that what we're really using here is we're in a sense using the fact that the 1D Sobolev inequality is very strong. Right. So the idea is that this is energy bound in 1D. This gives you like C0 bounds. In fact, more than C0, but So in other words, controlling the energy really does control the parameterization, which is, of course, impossible for the length. And we'll see sort of a similar thing in 2D. Okay, so this is just maybe a final thing about the GD6, right? If you actually now look at this functional and compute the Euler-Lagrange equations, so you can compute the Euler-Lagrange equations of E, right? So, right. I mean, to do this, we can allow any variation that is leaves us inside of this manifold M. So the point is, the energy when you do the variation, you're going to get some kind of second derivative term when you do the integration by parts. But the point is, you're not allowed to take any variation if you have this constraint M. So if you work it out, you get that the sort of the Euler-Lagrange equations are that gamma double prime of t is equal to some function q, which depends on the constraint manifold M, and this is a function of gamma and gamma prime, some kind of quadratic, some kind of polynomial in these expressions, which of course this is identically 0 if M is some Euclidean subspace. So we can very easily satisfy it in that case, since we know the critical point should be GD, unit speed GD6, and those are straight lines. But I think the point I wanted to make from the PDE point of view is that this is a nonlinear system of equations in general, but the point is it's what you would call, elliptic is not makes sense, but the point is it's semi-linear in the sense that the nonlinearity is lower order than the highest order of the derivative. So maybe as an exercise, right, if you go back to the length functional and you fix a parameterization and you just consider variations that are perpendicular to the curve, right? So if you look at that, you can compute the Euler-Lagrange equations of the length functional, and you should see that it's a different type of ODE, in the sense that it's more quasi-linear in a sense. But that's Oh, and I should say, of course, just a remark. Of course, I don't want to write this down, but of course you can explicitly figure out what this is in terms of the geometry of M, right? It should involve essentially the second fundamental form. But from our perspective, we don't need to worry about that. And of course, all of this can be done intrinsically in a Riemannian manifold, but I think this is easier to conceptualize. Okay, so that being said, now let's try and do the analog for surfaces, right? Okay. Okay, so in contrast, right, in one dimension you could take basically your only interesting, model is an interval or a circle, but obviously we know that for surfaces we have lots of different topological types, but locally, sort of the analog of the interval should be the closed disk. So let's focus on that for initially. So similarly, let's look at a curve capital gamma, which takes a closed disk now to some submanifold of some big Euclidean space. And let's suppose that this is smooth on the interior. So I didn't talk so much about this in the case of curves, and it's continuous up to the boundary, right? Continuous, yeah, let's say it's continuous. Okay, so then, of course, if you do some standard formula, that somehow the area of the image should be, this is just, one has to interpret this for a general smooth map, but this is supposed to be the integral over the disk of the following expression, which is the x derivative of gamma, right? This is a vector valued guy. The y derivative of gamma, and then you subtract the cross term. So, right. So remember, gamma is a vector valued function, so we can take its norm and its dot. These are the Euclidean dot product. Okay, and this is just D, the area form on the disk. So the reason this is the area, right? And the point is, I mean, this corresponds to the actual area when gamma is an injective immersion. When you think of things as a submanifold. Right, and again, I mean, since this is really only depending on the image, right? This is diffeomorphism invariant. So. Okay, so if we wanted to find a kind of, if we wanted to actually find, say, critical points of this functional by, say, a direct minimization procedure, or at least to analyze better how, say, the area controlled the parameterization, I mean, we can't just use the area. We're going to have to introduce some analog of the energy, something that is not parameterization independent. So again, here one makes the following sort of observation, right? So if you take this expression and rewrite it, right? This is this expression star. Like star is just the same as the length of the partial derivative of gamma squared plus the partial derivative of squared times sine squared theta gamma, where this is sort of the angle. This is the angle between. I mean, this is just reinterpreting what this means between del x gamma, del y gamma. Okay? So the observation is, first of all, this thing is maximized precisely when the angle is pi over 2, so when these guys are orthogonal. And, we don't like this expression, so we want to kind of, if we just had this expression by itself, so let's say star is with the square root, so we have square root of all of this, so we can, let me just make star have the square root. Right, so the point is, we don't like these two expressions, but we can sort of separate them and then get nice Dirichlet expression, sort of the energy, right? So this point is this is less than or equal to, by using elementary identities, this is the less than or equal to 1/2 del x gamma squared. Right, so you have equality if and only if, right, the del x gamma dot del y gamma is equal to 0. In other words, the angle, if you like, between them is 0, and the length is the same. Right. In other words, and here it's a subtle point, right? I mean, I'm cheating a little bit here. So, right, this angle, if the map is not an immersion at a point, this angle is not defined, but it's defined everywhere else. It's defined anywhere it is an immersion. But definitely this inequality holds it holds trivially at a point that's not an immersion. So what we observe from this is that sorry? No, so that's the whole, so I put the square root here, and then I kill that term, and then I have this term times this term with no square, but then I use the absorbing inequality, so AB is less than or equal to, yeah. So this, right, that's the, All right, so the upshot of this is if we define this sort of energy of a parameterization to just be the integral over the disk of now 1/2 del x gamma squared plus del y gamma squared dA, then we see that the area of gamma is less than or equal to the energy of gamma. And you have equality if and only if gamma is a right. So by the way, we're using the Euclidean area element on the disk. So we're thinking of the disk as like the unit disk in R2. Right. So if and only if gamma is what you might consider. Right. So if gamma is really an immersion, then this just means that the metric you pull back from the ambient space, so Rn, by gamma is just a constant multiple, a function that's a multiple. It's a scalar multiple of the Euclidean metric. So since we allow we do allow that gamma not be an immersion, we say that this. So that still makes sense. It's just it's allowed to be a zero multiple. So we say this is weakly conformal. Okay, so then, the observation now is that and this is where we make contact with the theory of Riemann surfaces. So the observation is this Dirichlet energy. I mean, this is just, if you just work it out component by component, but if you take each component of gamma, that's just this Dirichlet energy of the component, and you're just summing those all up and dividing by half. So the point is that is a conformally invariant quantity, right? I mean, it doesn't depend on the conformal class of the metric. It doesn't depend on the representative of the conformal class of the metric. And, this is sort of being captured in the fact that this is weakly conformal in a certain sense. But the upshot of all of this is that actually, the Dirichlet energy makes sense on a Riemann surface. So, the point is, if instead of just thinking about the disk, right, we just think of a gamma that takes some Riemann surface to M, right, then we can still talk about the energy of gamma, which is just, the integral over x of this. Well, I'm not going to write out. You have to interpret this, but it's just the right. You basically. Not x, gamma. Right, you just do component by component these. Well, maybe I'll just to make contact with what actual notation I used before. This is just the sum. This is the sum I equal 1 to capital N of this sort of gamma I. So this is the ith component of gamma in this Dirichlet norm. This square of the Dirichlet norm. This is this Dirichlet norm of x. Okay, and so then, what one is going to try and kind of in analog with the case of GD6, right? Clearly, one still has to do something analogous to this, but essentially, the idea is if we want to find, say, an area minimizer where we fix, say, the boundary curve, then it should be enough to find an energy minimizer. But of course, the energy, as you can see, is not a diffeomorphism invariant, right? So the other thing, which again, one has to do some computations, but in fact, you can actually make an analogy. You don't just need to look at the minimizer, you can also look at the critical points. So let me just make a remark. Okay, so so given this energy on a Riemann surface, so given this energy E on this Riemann surface X, right, the Euler-Lagrange, the critical points of it, so the Euler-Lagrange equations of this functional are again this Laplacian of X applied to gamma, so applied component-wise, plus, which is equal to some nonlinearity that depends again on the target, which is depends again on the value of gamma and the value of its first derivatives. And of course, this is identically zero if M is a Euclidean subspace. But what's interesting here is, of course, I mean, you know, for GD6, this was just we knew exactly what all the solutions were. They were just affine functions, whereas now they're just harmonic functions, and of course, there's lots of those. So studying harmonic maps into Euclidean spaces is somewhat is not completely trivial. And as we'll see, that means that studying these sort of minimal surfaces, which are related to these, are also non-trivial. Okay, so this such a gamma is called a harmonic map. Right, and so the observation here is that, right, this is now a system of elliptic PDEs because it's an elliptic operator. Well, given an E on Riemann surface, I can fix, that's what I don't like. So fix a metric in the conformal class. Right. So the functional is invariant under a conformal change of metric, but I'm a little bit I'm a little worried about the structure of the nonlinearity. So I think you can make sense of you should be able to make sense of everything without choosing a metric, but I'd rather be more careful. Certainly, if it's zero, then it makes sense, just in terms of the Riemann surface. But I don't usually think about it that way, so I'm not 100% sure. Okay, so the point then is, right? I mean, this is an exercise, but so you should maybe do this as a computation, right? So if gamma is an immersion, then is an immersion and is, say, critical for area, then this implies that, on the one hand, right, you should check that the mean curvature is identically zero. So remember, the mean curvature is just the sum of the principal curvatures. And then the second thing is that so the mean curvature is identically zero, or rather, the mean curvature is perpendicular to M. So if M is Rn, then that means the mean curvature is zero. But in general, it means the mean curvature is orthogonal to M. And two, you should check that in fact, at least in this immersion case, that in fact the map gamma. Well, let me make another. Let me actually move on. So this is just a differential. So this is identically zero if M is Euclidean. And I guess the point I want to make before I move on, though, is that this mean curvature, I mean, this is really a sort of quasi-linear equation in terms of the parameterization gamma. And it's also, I mean, you see It's not strictly speaking elliptic, of course, because also, I mean, you can reparameterize gamma, and it should also be a solution. So there's in a way, this is a much nicer operator to consider for that reason. Yep. QM is just some nonlinearity that depends on the manifold M. I mean, you can work it out. It involves the second fundamental form, but I don't want to write it down precisely.
So it's some expression which involves coordinates and...
Well, it should be. I mean, it's supposed to be. It's essentially. I mean, it's essentially the. I mean, you work out the Euler-Lagrange equations, and the point is, if you're forced to live inside of M, then you don't get to take your full. You don't get to take every variation. You have a constraint on the variation. So this constraint, this is sort of coming from the constraints. And if you want to work out, and you can work, but the point is it's the geometric problem, so the constraint should be coming from the geometry of the target. So essentially it should be the second fundamental form kind of evaluated at d gamma, but at the second fundamental form at the point gamma, the image of gamma, up to a sign, and you have to interpret everything correctly. But does that make sense? I mean, another way to say this, which is another way to say this is this is going to be a vector which is always orthogonal to M, and it turns out to be enough to just say that this is this similar to the fact that the mean curvature is perpendicular to M. It's kind of enough to say that this is perpendicular to M. So the point is, this is some value that's anyway. I didn't want to write it down because it requires talking about things that were not what I was going to mention, and all of this is interesting when this is 0 anyway. So, but yeah, it's like the second fundamental form basically. Okay, so anyway, so the point is let me just say, something like this is called a minimal immersion. This guy is this mean curvature being 0 or perpendicular to M. This is called a minimal immersion, which is a little bit of a misnomer. And the image is maybe a minimal surface, but so of course minimal. We're saying minimal, but it's really just a critical point. But of course, maybe it's better to say it's stationary. But anyway, the observation. I mean, the point I wanted to make, kind of connecting with the energy, is that if we want to find these guys. Right, so then, sort of one should check this, but that if gamma taking, say, a fixed manifold X to M is so is a minimal immersion. So in other words, an immersion, which is a critical point for area, or equivalently has this mean curvature property. And then the point is this should be sigma in the way I set it up. Then the point is they're supposed to exist, this is just a surface now. Then there exists a Riemann surface, X, and a diffeomorphism phi that takes X to sigma, such that if we compose gamma with phi, then the point is this map is supposed to be a weakly conformal, a conformal now. Conformal harmonic map. And conversely, any conformal harmonic map is a minimal immersion. Okay, So that's something you have to compute. But the point is, going back to this idea about the minimum, at least, there's a very clear way to see this is that, right? So this analog of this result I said for curves, so this is again, the proof is essentially the same as the one I gave, right? By the uniformization, let's just think about the situation for disks, right? So suppose gamma takes the disk to not a is say area minimizing, right? So and there's a little bit of a subtle point here, but I'll gloss it over. By the uniformization theorem, and it's important that it's an immersion. By the uniformization theorem, right? So just because it's area minimizing, there's nothing. This map does not need to be conformal, right, with respect to the usual way you think about D. But it gives us some. You can pull back the metric and get some Riemann surface structure on the disk. And then the point is, by the uniformization theorem, you can turn that. I mean, there's a subtle point, which is this is just topologically a disk. Why is it actually conformally a disk? But that's not so hard to deal with. But so you can change that to, by the uniformization theorem, there exists a phi that takes D to D, such that gamma of phi now is conformal, right? So the point now is that this area of gamma is now equal to the energy of gamma composed with phi, right? So the point is, if we had an area minimizer which was an immersion, then we could do this argument. I mean, there's a little bit of a technical issue about the extension to the boundary, but let's ignore that. Then you could reparameterize the curve and get that the energy was the same as the area, right? So that means that to find an area minimizer, in some sense, you would hope to be the same as finding an energy minimizer, which, as we would expect, is simpler. But the problem is this immersion condition is in the GD in the curve case was it was a technical thing, but we could sort of ignore. In this case, it really is this is really way too much to expect. So the point, though, is that you actually can get around it because you have this analog of the thing that I said, which is that you have this following proposition. You have this following proposition, which is just like what I said before, which is that for all epsilon greater than 0, right, if phi taking, say, the closed disk to D to M Rn, then there exists this should be gamma. Then there exists a diffeomorphism phi that takes D to D diffeo, such that the energy of gamma of phi is less than or equal to 1 plus epsilon times the area of gamma of phi, which of course is just 1 plus epsilon times the area of gamma. Right. So in other words, this idea is fine, even though we don't have an immersion. And the point is, we really do. I want to maybe convince you in the last a little bit that we really do have to worry about this issue of immersions. Okay, so this presents a strategy of how you might want to solve the question of finding a given minimal surface with a given boundary. So in other words, is to find the area minimizer, and as we saw, the direct method is not going to work very well there, but it will work pretty well for energy minimizers. At least that's what one would expect. I mean, I just want to make some remarks. So some remarks. So the first one is that in 2D, all right, the energy is less coercive, or is less strong, controls less. Let me say. Right. So the easiest way to see this is let's think of the upper half space model of the disk. So this is conformally the same as the disk. So in here we have this following sequence of maps: phi n of z, which is equal to nz, right? Right. So this just takes the half space and kind of scales it, right? So the point about this guy is these are conformal, right? And so if we think of them as now as elements of the conformal group of the disk, which you can do, then you observe that given any curve, the energy of gamma of phi n is the same as the energy of gamma. This is just the conformal invariance of energy. This is the conformal invariance. Right, but obviously this is taking the whole disk is sort of, I mean, any point in when you work it out, this is really forcing the gamma to essentially converge, locally to a point, to a constant map. Right, so this is really bad, right? I mean, because this means we can't possibly, if we don't somehow deal with these symmetries, we're in a lot of trouble in trying to do any kind of direct method. So just as we saw, like in 1D, we had the energy controlled the C0 norm, and that was the Sobolev embedding. So this is actually related to the fact that in 2 dimensions, the Sobolev embedding, just fails to control C0, right? So you may know that, like if you have a L2 bound on the energy of a function, you'll never be able to control its L infinity norm. But you kind of just barely fail to do so. So this is very closely related to that. The other problem is, as I said, I mean, this issue with immersions are somewhat problematic, right? So if you just consider the map z goes to z squared, that takes the disk to the disk, right? If I have a conformal harmonic immersion gamma, so in other words, at a minimal surface, and I consider, let's call this like psi, say, and I consider gamma of psi, right? That'll be a weakly conformal, but it'll still be harmonic. So the point is, this is going to be away from the point 0 where we have a branch point. This will be a perfectly well-behaved minimal surface. And this means that we definitely can get immersions. Of course, this is not going to be minimizing in any sense, but it can arise. So this is an example of what you might call like a false branch point, where we just sort of introduced it by reparameterizing in a bad way. However, there really do exist like true branch points where you really see a branching behavior in the image, and you really don't have a smooth surface. And in fact, if you consider a high codimension, they really have to arise even as area minimizers. So recall we had this set P, which was say W1 cubed equal W2 squared, which was a subset of C2. So this is the surface. Right, and you should convince. I mean, like I think Hayo mentioned. I mean, this really is area minimizing in a very strong sense. Like no matter how you change the surface, you increase the area. The point is, if you consider this P intersect the unit ball in C2, so this is maybe the unit ball in R4. Think about this in R4. Then you can parameterize that by z goes to z squared, z cubed, right? And this is mapping from the unit disk into this C4, C2, right? And you should see that the boundary goes, if the modulus is length 1, then I guess this is length, well, let's multiply it by 1 over square root of 2 to be, right? So this is a parameterization of this guy. And the point is, I mean, this is definitely area minimizing because this guy, I mean, it's certainly area minimizing in the class of disks because it's already area minimizing in a much bigger class. And so this tells us that at least in, I mean, we definitely have to get immersions at least at some points when we try and look for an area minimizer, at least if we look in high codimension. Okay. Okay, so then let me just kind of finish with just a statement of, maybe I'll briefly discuss this tomorrow, and then I'll also want to kind of discuss a different example of where you use Riemann surface theory to study really the most classical setting of this, which is in R3. But let me just pose a problem, which is this goes by the name of the Plateau problem, which is he was a Belgian physicist who was studying sort of soap films, and it turns out that, I mean, these area minimizers are a good model for soap films, so that's why he introduced them. So the idea is, say, given a reasonable curve, what that means is, say in words, takes the boundary of the disk to. So Plateau only formulated this in dimension 3, but we might as well do it in general. Which bounds some finite area disk in M. Right, so this automatically, this is to bound a disk is a topological condition. To find a finite area disk is a somewhat subtle geometric condition. But it's definitely satisfied if, for example, this is null homotopic and C1. So that's what the reasonable means. Because so then the question is, the first question is sort of existence. So does there exist a map gamma that takes the closed disk to M, which is area minimizing, which minimizes area with respect to having the boundary conditions be given by gamma. So then there's a regularity question. If such gamma exists, can we take it to be a weakly conformal harmonic immersion, harmonic map, let me say. Sorry, I don't want to say immersion. And then maybe just the final part. So there's a kind of stronger regularity, which is so when is and since we already know in general this can't be true, so when is gamma, say, a minimal immersion? Okay, so right, so I'll at least give some ideas. I mean, you can sort of see the idea of the proof, which is to try and use this energy minimization. but it's definitely more subtle than that. So I'll discuss this a little more next time. But let me just say that given this question, so Jesse Douglas and Tibor Rado, they solved this part, at least when M was a Euclidean space, and then Mori solved it for a general manifold. So they proved that with some additional conditions, this guy has some, it's like, this is good at infinity. So they proved that they established such a solution that satisfies these two things would be called a plateau solution. So they established the existence of a plateau solution. So they established there was a minimizer, and they established that the minimizer had this following regularity. You could choose it to be a weakly conformal harmonic map. In other words, a minimal immersion away from a finite set of branch points. So what was interesting is they proved that. I mean, Jesse Douglas got the first Fields Medal for it in the 20s. So there's a big gap between when you could try and say anything more about this type of question. So this was solved maybe in the 60s or 70s by Gulliver and Osserman, and so they proved that in fact when you're in codimension 1, so in other words in a 3 manifold, or even in R3, it's interesting. They proved that actually you didn't have any of these interior branch points. So actually you were a minimal immersion. So that's a very nice result. And the point is this result, that their proof is really quite interesting because it really uses some global minimization properties. So the final thing, which maybe I'll stop here. So you could ask an even stronger regularity question, at least in codimension 1, which is, when is the image actually smooth as a, say, submanifold? So that would, I mean, if it's a minimal immersion, the only way it could fail to be smooth as a submanifold is if it crosses itself. So, and of course it has to, you can convince yourself it has to cross itself for lots of curves. For example, if the curve is knotted, like the trefoil, should bounds a minimal immersion, but it's certainly no way to make that embedded. So that's actually, a quite subtle question, which was solved, I guess, solved by a number of people, but the one that's probably the most in the spirit is by Meeks and Yao. So they proved a stronger result, but the easy to understand result is that if gamma lies in its convex hull, in the boundary of its convex hull, then it has to be bounded. At least the plateau solution you find is actually embedded. So that actually means it's as regular as you could like. At least in the interior. But I'm out of time, so I'll stop here.